Well, here are the sample problems for class 22 of Math 117, and I'm going to jump right in and derive the Black-Scholes equation for the case where the interest rate is 0. Remember the Wiener process. This has the property that it's normally distributed and the variance is proportional to the time. And what you've proved about this is that W sub t is a martingale, W sub t squared minus t is a martingale, and best of all, the exponential of minus sigma squared t plus sigma times W sub t is also a martingale. And that's going to let us figure out the value of a call option. What do we have to do? We've got to take the value at time t when it matures, which is the price of the underlying share minus the strike price, but only if that quantity is greater than 0. And we can write a formula now for this price. It's the price at time 0 multiplied by the exponential of the quantity that does a random walk with this extra drift e to the minus sigma squared over 2 times capital T added to it. But the random walk part is sigma times the square root of t, that's the standard deviation, times a normally distributed random variable y. And what I have to do is to subtract k from that, and then, this is the tricky part, integrate only where we're in the money. So our first question is, when is the option in the money? Well, that's going to happen, of course, when e to the minus sigma squared over 2 times t plus sigma root t times y, this exponent up here, is greater than or equal to the strike price over the initial fair market value. Now I'm going to try isolating y. I'll begin by taking the logarithm of both sides. So the exponent on the left-hand side is minus sigma squared over 2 times t plus sigma root t times this random variable y. That now has to be greater than or equal to the natural log of k over x0. And now I can solve this for y. Y has to be greater than or equal to, well, I'll begin by adding sigma squared over t to both sides. So I'll have the log of k over x naught plus, coming over from the other side, sigma squared over root 2 times t. And then I have to divide by sigma times the square root of t. I want to give this a name. Let's call it t sub 1. Okay, so now we can calculate the expectation by using the density function for the normal distribution because we know the lower limit of integration. The value of our call option is the integral from this lower limit t1 to infinity, that is over all the values where the option is in the money, of initial price times the exponential of minus sigma squared over 2 times t plus sigma square root of t times x minus k. And how do we calculate the expectation of that function of our random variable? Well, I used the variable of integration x, where I had a y before, and then we have to multiply by the density function, 1 over square root of 2 pi e to the minus x squared over 2, and we've got to integrate over x. When I did this in the R script, I actually did it as a Lebesgue integral, but here I'm doing what's usually done when you're doing a Lebesgue integral, but the probability density can be expressed completely in terms of a single density function. I'm doing the integration over the domain using the law of the unconscious statistician. Okay, now we're going to split this into two pieces. The first part is excluding the minus k bit. So I've got x0 over the square root of 2 pi times the integral from t1 to infinity of something that looks messy but is actually going to turn out to be quite manageable. And if you look at this as I write it out, you might say, hey, isn't that a complete square? Yep. So that's the first part. And then the second part is the term that involves the strike price. That's k times the square root of 1 over 2 pi times the integral from t1 to infinity e to the minus x squared over 2 dx. Now look carefully at the first part. There's an obvious substitution. I'll just set y equal to x minus sigma times the square root of t. Why did I do that? Because then minus y squared over 2 is what? It's minus x squared over 2. Well, we've got that. Minus sigma square root of t times x. We got that. Minus sigma squared over 2 times t. We've got that also. And because this is a simple linear change of variable, dy and dx are both equal. The only thing we've got to worry about is the lower limit. The lower limit on x was t1. The lower limit on y is t1 minus sigma times the square root of t. So let's work that out. t1 has this 1 over sigma root t in it. Then looking up a few lines, we've got log of k over x naught plus sigma squared over 2t. But we've got to subtract off sigma times the square root of t. That's already in the denominator outside, so we've got minus sigma squared without the over 2 times t. Or, if you prefer, 1 over sigma root t times log of x k over x0 minus sigma squared over 2 times t. Well, we're almost done. The one other thing we have to notice is we are doing our integrals from some lower limit to infinity. But the normal distribution has a symmetrical density function. It doesn't make any difference whether I integrate from a to infinity, or instead I could do this formally by introducing a new variable equal to minus x. Do the integral instead from minus infinity to minus a. In other words, compute the function that Deneen calls capital N. That's the probability that random variable x is less than or equal to a. So we can write down the Black-Scholes formula. First term, we've got an x0, and we've got a normal distribution over y, where the limit of integration is now 1 over sigma root t. That had a minus sign in it because we've got n of minus a. I'll introduce the minus sign on the logarithm by just flipping the argument over. Then we had a minus sign here. That changes into a plus sign. So that's the first term. And the second term was already in exactly the form we want. We've got minus k times the distribution function for the normal distribution evaluated for minus t1. And again, since it's minus t1, I flip over the logarithm, log of x0 over k. In t1, that showed up with a plus sign. Now here it shows up with a minus sign, and we've done it. That's the Black-Scholes formula for pricing of a call option. So you ask, how do we use this? Well, let's imagine a practical situation. You got your startup company going to keep your employees happy. You give them some call options. You want to have them stick around for a while, so you make them mature 4 years in the future. Let's assume a risk-free interest rate of 5%. The Fed is sort of moving in that direction these days. Your stock is currently priced at $18.10 a share. You give the options a strike price of $20, and the volatility is 0.2, which means that the variance over time is going to be 0.04 times t. Well, when you do this, these employees are getting something of value. The IRS wants to know about it, and so you have to specify the fair price of one of these options. And the way you do it is by plugging all the data into the Black-Scholes formula. I have written a nice little R script, wienermodel.r, and in that I've included the Black-Scholes formula with the extra term that has to be added if the interest rate is non-zero. And if you look at the rewrite at the bottom, you will see that effectively what's happening with this formula is every time I have the strike price k, I replace it by the discounted strike price k times e to the minus rt. That happens in 3 different places. Well, no one wants to do these computations by hand, so let's have R do the job. I haven't tried this, but let's hope it works. So we bring up our studio, bring up the Wiener model file, scroll down to find this nice little formula. And define this function. A word of warning, by the way, here. If you want to break up a line of code in R, you should end the line with a minus sign or a plus sign or some other operator. If you move this minus sign down onto the next line, things will fail in a thoroughly mysterious way. So let's define this function. And then let's call the function, and in this particular case, the current price is $18.10. The strike price is $20. The time to maturity is 4 years. The interest rate is 0.05. The volatility is 0.2. I call that, and down at the bottom of the screen, I get the answer, 3.67 cents. So that's the current price. Well, I failed to paste it in, but you saw how I did it. Okay, so that's number 2. So the third problem is a repeat of the second problem, not taking advantage of the proof in the first problem. How could we work out this calculation of the fair market value if we didn't have the general Black-Scholes formula? Well, the first thing I'm going to do is to set mu equal to R. That is to say, I'm going to assume that prices generally drift up in accordance with e to the RT, because that's the effect of a risk-free interest rate of R. And in that case, I can say the value at time t is going to be e to the mu t times what we're given by the Black-Scholes formula, x naught times e to the sigma wt, that's the random part, minus sigma squared over 2 times t. But mu was equal to R. You already know that this exponential is a martingale, and I can rewrite this by moving e to the minus r, by moving e to the RT to the other side, and say the discounted value of the price at time t is equal to the initial price times e to the sigma w sub t. That's a random variable, minus sigma squared over 2 times t. That's a constant, and what we know is that this is a martingale. So the discounted price is a martingale if you have a non-zero interest rate. What about WT for 4 years? Well, that has variance equal to t, which is 4. I picked 4 because it has a nice neat square root, namely 2. So if I take y defined as W4 over 2, that's going to have a variance divided by 2 squared, variance 1, expectation 0, and it's normally distributed. In other words, it's an n0, 1 random variable. To be in the money, we need this quantity x4, the price after 4 years, to be greater than or equal to k. In other words, x0 times e to the sigma times w sub t, which is now turned into 2 times y, times e to the 4r. I've moved that factor over to the other side of the equation, minus sigma squared over 2 times 4. That has to be greater than or equal to k. If I solve for the exponential of the quantity involving y, I get k over x naught times e to the minus 4r plus 2 sigma squared. Now we've got some nice neat numbers here. First I'll take the logarithm. 2 sigma y has to be greater than or equal to log of k over the initial price minus 4r plus 2 sigma squared. But I chose k and x naught so that this first logarithm is 0.1. The second term is equal to minus 0.2, and the last term is plus 0.08. Put it all together, and you've got minus 0.02, and therefore I can easily figure out what value of y I need. I need y to be greater than or equal to minus 0.02 over 0.4, which is minus 0.05. This is the quantity I called T1 in the general derivation. So now we've just got an integral to evaluate. The expectation of the discounted price is going to be the initial price over the square root of 2 pi, that's from my normal distribution, times the integral from minus 0.05 to infinity of e to the what? Well, I've got an e to the minus 0.08. That's from my 4 times sigma squared over 2 times e to the 0.4. That's 2 times sigma. I replace my random variable y by the variable of integration. I multiply by e to the minus y squared over 2 to complete the density function. And then I've got a similar term with the strike price over root 2 pi times e to the minus 0.2. That's the discounting factor. And again, the integral from minus 0.05 to infinity of e to the minus y squared over 2 dy. What are we going to do with this first term? Well, you know, because you've seen the general proof, that that exponent is actually a perfect square, and I'll just introduce a new variable. Set x equal to y minus 0.4. Why did I do that? Because then minus x squared over 2 is minus y squared over 2 plus the cross term 0.4y. You can see these things are already sitting there in our integral. That's the exponent we already had. Wow, that's great. So what's the lower limit? The lower limit for our new variable of integration, x, is minus 0.05 minus this extra 0.4. In other words, it's minus 0.45. And we're nearly done. The expectation of the discounted value of the option is the sum of two terms, x naught over 2 pi times the integral now from minus 0.45 to infinity, e to the minus x squared over 2 dx, minus k times e to the minus 0.2 over root 2 pi times another of these normal density function integrals, this one from minus 0.5 to infinity, minus 0.05 to infinity. Different name for the variable of integration, but who cares? And then remember that when you integrate the normal density function from a to infinity, you get the same as if you had integrated it from minus infinity to minus a. In other words, you get the function n of minus a. And in the pre-computer era, people carried around with them a nice table of the values of this function because it can't be expressed in terms of elementary functions. These days, you just use something like R to calculate it. Well, let's crank out a numerical answer. The expected discounted price is equal to x0 times the function n evaluated for the negative of 0.45 minus the strike price times e to the minus 0.2 times this normal distribution function evaluated again at the negative of that lower limit. And I've conveniently provided all the numbers. Initial price 18.1. This value of n, which I looked up. Strike price of k. This exponential multiplied by 0.519. I threw that all into a calculator. In fact, I calculated in R. And of course, because I did everything right, it took me a few tries to get this completely right, by the way, I got the same answer as on the preceding page. This is redundant, but I think you learn a lot about the Black-Scholes equation by working a specific example like this. So let's send this off to YouTube.